Dear all, welcome back to the graph series. So in today's series, we'll be starting the shortest path algorithm. So whenever we study graph, we actually deal with paths. And why do we use graph? Suppose you want to travel from one city to another city. So we want to find the shortest path to travel from one city to another city. So in those scenarios, this plays a crucial and important role to find the shortest path. And for that, we have three types of algorithm to deal with the three types of shortest path. So let's see the shortest path algorithm in detail. So what it tells that in graph data structure, shortest path algorithm calculates the minimal distance or cost to reach nodes within a graph. That means in shortest path algorithm, we always have to find the minimum distance. Let's say we take this algorithm, we take this graph. So we want to traverse from this. Let's say this is city Kolkata and we want to traverse from city Kolkata to city Mumbai. So there are two ways how we can traverse in this graph. Either we can traverse like this and then we can traverse like this. So what will be the distance? Let's say this is 1 and this is 1. So the total distance from here we will be getting that is 2. And let's say we are traversing like this directly through this and this is also 1. So here the distance is 1. So now if we just compare the two tracks, we get the minimum distance here, that is 1. And that is the core object, that we always have to find the minimum distance of shortest path algorithms. So whenever we study the case of shortest path algorithms, we have three types of cases. That means in graph we deal with three type of cases. First, we will be getting non-weighted graphs. Second, that is weighted graph. So you might be thinking, what is non-weighted? Now observe the graph. This graph 0, 1, 2, 3. Let's say this is connected like this. So this graph is now connected. As we connected, so if the graph, the path, this edge is not having any cost or it's not having any specific value, that means it is not having any value provided, that means then we call it non-weighted. That means a graph which is not having any weight, that is called non-weighted. So whenever we deal with non-weighted type of graph, we always take the default value as 1. That means in non-weighted graph, the default age value is always considered as 1. So if that is non-weighted graph, if we just encounter is non-weighted graph, then the age value that we'll be taking for only up to one level, up to that level, that will be 1. And others that we haven't traversed, let's say there are more nodes like this, there are nodes. So these are also some nodes and these are also some cities, you can say. So we'll be just representing them like this, -1. That means we don't know what is that distance, that means non-reachable. Here we use -1 to represent non-reachable state, that means that position is non-reachable. So this is the non-weighted graph case. Second, the weighted graph case. So weighted graph, that means the graph which is having its weight, which is having its value. So let's see the other cases. Suppose this graph 0 to 1. So if we want to traverse from 0 this location to this location, so for that we have to, let's say we have to pay 5 rupees. Let's say we want to come 0 to 2, we have to pay 4, and for 0 to 5, let's say we have to pay 10. So you see there are a different type of values, and that is the case of direct weighted graph. That means we will have an weight, we'll have a value cost to move from one space to another space. Okay, now the third case. Let's say in this case we want to traverse from 1 to 0. 1 to 0 we want to traverse, and it is having a negative value of 10. That if you transfer from 1 to 0, then 10 will be provided to you. So notice we get a negative value here. So and now you want to traverse like this 0 to 4. So let's say it is having 4 weight value, and 0 to 2, this is 5. So the important things to notice here, that we are getting a negative value. And let's say again to reach from 1 to 4, we have to pay -4. So the first things where you are just observing positive, this is called weighted graph of positive case, that is positive weighted graph. And the third case that you are observing, that is called negative weighted graph. That means while we find shortest path algorithm, we actually deal with three type of condition. One, non-weighted condition, second, weighted and positive condition, and third, negative weighted condition. So these are the three type of condition. So to deal with three type of condition, we actually use three type of application. When we get non-weighted graph, we use the BFS shortest algorithm. In that case, we utilize the BFS shortest algorithm. That means the the algorithm or the strategy we apply utilizing BFS, that is called BFS Shortest Algorithm. So we'll be implementing it in today's video session. Dijkstra algorithm, when you get a cases like this, that only there are positive weights, not negative, only positive, all weights are positive, then we'll be utilizing Dijkstra algorithm for positive weighted graph. Positive weighted graph. It don't work on negative weighted. When you get a negative cases like this, we have gotten here a negative case. So in that case, negative cases will be using Bellman-Ford algorithm. To deal with the negative cases, we use negative weighted graph. We use the Bellman-Ford algorithm. And flood reversal algorithm is also utilized in the shortest path algorithm. So in today's video session, we'll be observing the BFS shortest algorithm. I mean non-weighted case when a graph is not having weight. So let's say this graph is connected like this. First, this 0, we can call it any city or any nodes or anything in connected. So 0 is connected with 1 and 2. 0 is connected with 2. 1 is connected with 3 and 4. This one. 2 is connected with 5. And let's say 4 is also connected with 5. 3 is also, let's say, connected with 5. Let's make it look beautiful. 3 is also connected with 5. So we make that type of random graph. So what is our core focus? That we have to find the minimum distance. Let's say we have to find the distance from 0, starting from 0 to 5. So we have to find all the cases. So we have to think that how we can apply. So here first thing you have to notice that we will be applying BFS. BFS, that means a level order traversal type of things. BFS, that means a level order or breadthwise. That means we'll be traversing like this. So whenever you get that type of traversal, we always use one single data structure, and that data structure is QE. We use QE to represent that type of data structure. That means to implement this shortest path algorithm, we'll be using a QE. QE. Second thing, look, whenever first we have, by default in shortest path algorithm, we take the weight as 1. Weight as 1. This is the default that we take in the shortest path algorithm. So let's say we want to traverse from 0 to 1, so it will have a weight of 1. Want to traverse 0 to 2, it will have a weight of 1. So they are connected. Now notice this 0 and 4. The relationship of 0 and 4 is not connected here. In that case, we will be initializing the 0 and 4 relation by -1, by the cases of -1. So we'll be calling it -1. That means that is not reachable. 2 and 4 will be representing 2 and 4 by this like -1. So we can represent, that means these are not connected, these are non-reachable. So by default we'll be using positive one to represent that there is a connection of two nodes. Two nodes are connected, that means they are represented by +1. And if two nodes are not connected, then we'll be representing them as by the relationship of -1. That means not connected. Not connected or not reachable. That means they are not reachable. Okay. So now you got the brief idea about the shortest path algorithm. So first we have to utilize the QE. So what we will be doing in QE, we'll be processing all the nodes one by one utilizing the data structure QE. So let's say we start from 0. So we'll be pushing this into the QE 0. We'll be pushing this element. So let's say we post from that side. So QE will be coming here. 0. Okay. So now we process 0. So whenever we process 0, we don't want to process the same data again and again. That means if we have processed 0, we'll be marking 0 such that the 0 has been visited by us. That means this 0 has been visited by us, we'll be marking. And for that, we'll be using an array. For that, we'll be using an array like visited array, let's say. So this is visited array. So this visited array will be keeping which nodes have been visited. If 0 has been visited now, so we'll be marking that 0 has been visited. We'll be adding here also. That means we have visited the 0. We will not visit once again. Got it? So once now we have inserted the 0. Now after entering the initiation or start node, now we'll be popping this element back. We'll be popping the 0 back. We'll be popping it back, and it will, now we'll be assigning it to our any node. Let's say node 0. We'll be assigning the value to node 0. So for this node 0, we'll be checking that if it is having connected nodes, it is having neighbors. Neighbors are those elements that are directly connected. So if you just notice, this 0 is connected directly with 1. This 0 is directly connected with 2. So they are directly connected. That means the neighbors of 0, are 1 and 2. 1 and 2. Now notice one thing, that if we have visited any element, let's say we have visited 1 previously, first we have visited in element 1, so we will not visit that again. So we'll make a case, we'll check that if this element is not visited, that means if not of visited, we'll implement a case like this. If not of visited dot that element, if that is not one is not visited, then only we will again pushing that one here. That means one will be pushed into queue, then two will be pushed into queue, because they are neighbors. And this is how we will be implementing this shortest path algorithm. So let's understand the algorithm in details one by one with code lines. That was the approach. That first will be setting 0, then 1 and 2, then we'll be adding this 1 and 2 in here also. That means we got visited. Now again in the second case we'll be popping this one back. So we'll be popping this one back, and for 1 we'll be checking from here. For 1 we'll be checking that who are connected with 1 directly, who are the neighbors. And for 1 you can see the neighbors of 1 are 3 and 4. 0 is also a neighbor. Notice 0 is also a neighbor, but 0 has been visited, so we'll be not encountering. 3 and 4 is not visited, so we will be adding 3 first here, and then we'll be pushing into 4 here. That means 1 has been popped. 1 has been popped, so 3 and 4 will be added to visited node. So for the, then after 3 and 4 is processed, now we'll be again popping. This is from queue, we call it poll, and stack we call it pop. So we'll be polling now 2. So for 2 we'll be checking it is connected with 5. So now we'll be processing 5. We'll be entering 5 here, and we'll be adding this 5 here. So for 5 we'll be checking it is connected with 4. It is connected with 4, but the important things that 4 has been already visited, so we will not visit once again. Okay, so that was quite random. Let's understand the code explanation. So whenever we implement that type of algorithms in graph, first what we have to do, we have to create this graph, the graph that you can see. We have to create the graph. We have to first create the classes, nodes, then we have to add the nodes like this using our graph code lines, and then we have to implement all the relations like this. Then we'll be processing all the nodes like this. We'll be creating a kiwi. This is kiwi that you can see. So we'll be creating that kiwi. We'll be creating this visited node, visited set, or array list, whatever you can see. So we'll be creating everything one by one. And to represent that type of things, that you can see, I mean, this graph, we always use that type of list. We'll be using that type of list, and we call it adjacency list. So this is adjacency list, and the important feature of this adjacency list is that it contains list. It contains list like this. So we'll be creating adjacency list like this. So let's start writing the graph class. So first we'll be creating the file name graph. So we call this function like public class, public class, and we'll be calling the file name as shortest graph traversal. So we can take any name as we want, but unweighted shortest path will be better for our question. So let's take public class unweighted shortest path. Unweighted shortest path. So this is the file name, because here we'll be tracking the unweighted shortest path. So first what we have to do, we have to, how many number of nodes we want to take, count here, 1 2 3. So how many nodes we want to take, so for we'll be declaring that number of vertices. So private integer number of vertices, private integer number of vertices. So we declare the number of vertices here. Once we have declared the number of vertices, then we will be creating this adjacency list. So private, and then we create a list, private list. This is the main list. We have created this list. Now notice this is also a list, and this list is a list which will be containing 1 2 those integer data type. That means list of integer. So we'll be writing that case, that list, this includes this small list, and this list include integers, integer, and we'll be calling this one adjacency list. So adjacency list. Okay, that's done. So every time we create that, those type of declare those type of variable, we initialize them inside a constructor. So let's create a constructor, public unweighted shortest path, public unweighted shortest path, and now we'll be passing the integer number of vertices, integer number of vertices, number of vertices. So now the number of vertices has been passed, and now we'll be initializing those number of vertices. So let's use this color. So now let's initialize this dot number of vertices. This dot number of vertices that equals to number of vertices. So from codes we'll be passing that 1, 2, 3, 4, 5, 6. That means if we want to add the 6 number of vertices, then we'll be passing those 6 number of vertices. Once we have initialized the 6 number of vertices, then we'll be initializing the adjacency list. We'll be initializing the values in the adjacency list for how many number of vertices we want to add. So we'll be initializing with respect to the data structure array list. So adjacency list equals to new, and we'll be initializing with respect to array list. New array list number of vertices. That means we'll be storing 0, 1, 2, 3, 4, 5. So up to 5 we'll be using creating adjacency list. So the number of vertices. Okay, so now we have initialized it. So by now we have created the constructor and our graph has been initialized. You can see we have initialized the basic core features. Now after we have initialized adjacency list, we have just created the space for this. By this code lines we have created this space. Now notice we have to add those small portions. So we have to add those. So for that, if we just simply run an algorithm to execute those all lines, it will work. So inside it we'll be executing that line. So let's run a for loop to create all those things. For that we'll be running a for loop like this. For integer I equals to 0, so we'll be starting I less than number of and then I plus plus. So we'll be running this for loop, and in this for loop we'll be creating the new array list with respect to every adjacency list. So adjacency list dot add this adjacency list, this. So adjacency list dot add, and here we'll be adding one more new array list, and this array list will be containing integers. So we no need to actually declare, we have declared. So if we just pass the generic type, it will be okay. Adjoint list dot add new array list. So okay, by now we have initialized all the things that we require. So we'll be closing this for loop, and then we'll be closing the constructor also. So now we have closed the constructor. That means we have created this node. That means this has been allocated, this portion has been allocated. Those small segments that you can see here, those has been created, okay. So now we'll be moving to the next section, that will be adding a age, public class add age. So now notice, if we want to add age, so how we are representing in adjacency list. In adjacency list, what we have to do, that suppose this is connected, 0 and 1 is connected, and these are not one way directed, that means connected. So they are connected from both sides. So this representation will be like this: 0, 1, and they will have list, and they will contain all the connected nodes. So 0 is connected with 1 and 2, so it will be containing 1, 2. 1 is connected with, let's say, 3 and 4, so it will be containing 3, 4, and 1 is connected with 0 also, 0. So they will be containing this one, and for that we have to add those age in both. Let's say this is U section, we have to add in U, and let's say this is V, so we have to add in V section. So for that we'll be create a function add age. So let's create a function, and first let me just remove this section. Okay, so let's create a function public void add age, public void add age, and we want to add 2 points. Let's say we want to add this point U, and we want to add this generalized point V. So integer U and integer V. Okay, so we these are already all present in adjacency list. So we are working with respect to adjacency list. This representation that you can see here, this is the adjacency list, that is adjacency list. So we'll be working on adjacency list. So first we'll be fetching this U. using dot get. So we'll be just starting like this. Adjacency list dot get of u. And once we fetch the u, that is the initiation pattern matrix, then we'll be adding this source. Then once like this, we are fetching, let's say this u value, this is 0u, and once we fetched u, we are adding this v. So v, that means one will be added. So dot add of v. Okay, adjacency list dot get of u and dot add of v. So it will add the node, and then again we have added in 0th side, then we'll be adding for this v side also. We have to add from both sides, so we'll be adding adjacency list dot get of v dot add of u, and it will add from back direction also. So now they are added from both direction. Both from u side it is added with v, from v side it is added with u. So they are connected from both ends. That means we have created the edge. So now if we just run the program, call the function for 2 and 5, 2 and 5 will be connected. If we just call the function for 2 and 4, 2 and 4 will be connected. If you call the function for 4 and 5, 4 and 5 will be connected. So this is the void added function. So now we have implemented the void added function. Now we'll be implementing the BFS shortest path function. So for that we'll be writing the BFS shortest path, and it's very easy. So let's write. Okay, let's write the BFS shortest path in next page. Okay, so we start writing BFS shortest path. So here we'll be creating this QE because we have to execute our main array here. So we'll be creating this QE. Then we'll be creating this visited set. The visited set you can see here, visited set, or either we can use data structure of set, or we can use the data structure of array list, whatever we want. So we'll be creating all those sections here. So let's create the function first. First we'll be creating the function public void shortest path with respect to the start node. So let's create public void shortest path. And whenever we deal with BFS, whenever we deal with BFS strategy, BFS strategy, we are always provided with any start node, any start node. So it can be any start node, it can be any start node, it can be any start node. So we will be passing integer start node, integer start node. Okay, so now we are passed with integer start node, and now we'll be starting executing the program. So first of all, what we need to create, we have to create those queue, we have to create those visited set, and for that we will be creating all the things. And one more thing, we have to maintain the distance also, the distance from here to here, the distance from here to here, the total distance from 0 to 3, we have to track those also. So we'll be using one more array for this distance. To calculate the distance, we'll be using one more array, and we'll be initializing all the distances with -1, -1, -1, -1, -1, -1. So let's create that distance array. So integer distance, integer distance. So integer distance, this is the array, new integer, and we'll be creating up to the number of vertices, number of vertices. So we have created a distance array. Now we'll be filling the entire distance array with -1. We'll be filling with -1, this -1, to represent that is -1. That means we'll be filling with -1 to represent that not reachable condition, not reachable condition, not reachable condition. So now let's fill it. Arrays.fill, arrays.fill, and the array name. The array name is distance, and we'll be filling it with -1. So -1, that means the distance array is filled with -1. Now we'll be creating our QE. So we'll be using the data structure array DQ for it. So let's create QE DQ, QE. So this QE right now we are creating. So we'll be storing here integer, QE integer, and we'll be using DQ, that is equals to new array DQ, new array DQ. So we have utilized the array DQ data structure here that stores the integer, and then we'll be starting. So by now our entire array contains -1. So whatever the start node, we are provided with an start node. If we start from here, the distance from this instance to this instance is always 0. The distance from this to this is always 0. So we will be initializing the start node as 0. So let's say 0 is our start node. So we will be initializing it as 0. So we'll be simply writing like this. So we have created the distance array. So let's write distance distance of start node that we are assigning with 0. That means that is made 0. So that is made 0. Okay. And now we'll be start adding the node in our QE. So QE.add. So suppose we are provided, so we'll be adding this 0 in here. So QE.add QE.add. So we will be adding that start node. So once we run this QE.add start node function, this gets added. That gets added through this side. That get added through this side, and now 0 is present in our QE. So once the 0 is present in our QE, we will be start running our program of while queue is not empty. So I mean we'll be running the program until the QE again. First we insert 0 here, then if 0 is connected with 1 and 2, then 1 and 2 will be added. Then if 1 is connected with 3 and 4, 3 and 4 will be added. That means program will automatically add those numbers, and we'll be polling also. We'll be polling those data also. So until the queue is not empty, again it's not becoming empty like this, we'll be pulling this one. So for that we'll be using the while loop. So let's write this line, that while not of QE, while not of QE dot is empty. That means until QE is not empty. So we'll be fetching this first node into current node, integer current node that is equals to QE dot poll. So we are fetching this data QE.poll. So this is being coming, and this is getting assigned into current node. So now we will be exploring. Now we have fetched this 0 node, and we need to explore those neighbors 1 and 2 neighbors. So we'll be checking with respect to that current node. So like this, for that we have to check this one, this one 2, and 0 have its adjacency list containing all those information 1 and 2. So for integer neighbor, where we'll be checking in the adjacency list of current node. So adjacency list dot get of current node. So we are fetching from the dot get of current node. So now we need to check that if the distance of neighbor is still -1. So let's say this 0 to -1, and we will be checking the array, that if this array the distance is still -1, that means it hasn't been visited. So we can directly add it. So we'll be checking if we have initialized the distance array here. This is distance array. So we'll be checking this distance, that if distance of neighbor, if distance, we'll be checking. If that is not, then we'll be running the program. So if not of distance of neighbor equals to -1, equals to -1. I mean that means if the distance of neighbor is not -1, if the distance of neighbor is not -1, then we will be updating the distance of neighbor, and we'll be updating the distance of neighbor with the current value +1. So then we'll be updating the distance of neighbor. Distance of neighbor will be distance of current node, distance of whatever the current node +1. So if the current node from here the distance of it was 0, so now we'll be adding the distance with 0 to 1 like this, 0 to 1. So we'll be adding +1 here, so it will become 1, that is equals to 1. So this 1 will be added to this 1. That means the distance from 1 to 1, that will be 1, and it will be assigned like this. So we'll be storing that value. So after this line has been executed, we have found the distance. So after we find the distance, now we'll be adding those 1 and 2 to the QE. We have to add those. So we'll be writing the line, that QE.add neighbor, QE.add neighbor. That means we added that neighbor into the QE. Okay, so by now we have executed the main line of that. So after the while loop is entirely executed, it adds all those elements. It currently it visit all those elements after that line. Font is visit 0, then it adds 0, then from after 0 is again popped out, it visit 1 and 2. 1 and 2 is added here, and it's also added in the queuing. From 1 it checks 3 and 4. 1 is pulled, and if 3 and 4 is also added, then after 3 and 4, let's say 2 is connected. So when 2 is pulled back, 5 is then checked, and 5 is also pushed in here. 5 is also pushed in here again. If let's say 5 is connected like this, 5 is connected like this. So if again 5 is connected, we get the all values in here. This distance set we get to have the value. So whenever we get those values to have, we don't execute anymore. That means the entire graph is visited with shortest path, and in distance set we have the shortest path. So now what we do, that now we actually start printing the graph. So like this, system.out.println, system.out.println, and now we'll be writing that shortest distance from node, shortest distance from node. We calculate the shortest distance with respect to a start node. Let's say this is a start node, so plus start. If the name was the start node, so it will be start node. So this was the start node, this one. It will calculate the entire distance with respect to that one, shortest distance from that node. So plus this space, and now we'll be running a for loop for all the number of vertices, and all shortest distances will be here, like 0 to 1 the distance is 1 1, it will get stored here. Then 1 2 3 4, so 0 1 2 3 4, so the 3 4 distance might be 2 as per our approximation, 2 2. So this distance array is having all the values. So if we just run a for loop in this distance array, we'll get all the distances. So like this, for integer I equals to 0, I less than number of vertices, I plus plus. And now we'll be printing system.out.print system.out.print, and we'll be just printing the distance of I. So let's print the distance of I, distance of I. So we are printing the distance of I, plus we'll be adding some that type of to traverse that we are traversing in that manner. So okay, this is now we have implemented the entire graph. So after that, we will be just calling all the function from main. We'll be calling all the function from main. So we'll be writing the file for this: public static void main string of, and the file name was BFS shortest path, I think. So we'll be creating an object with respect to whatever the Java file name was. So BFS shortest path, BFS shortest path. Let's say the object is path. So path that is equals to new BFS shortest path. I just forgot the file name, whatever that was. So with respect to the Java file name, that is the Java file name, and we are creating this the object, and with respect to that object, we'll be calling the addEdge function. So path.addEdge, path.addEdge. So when we'll be calling this 0 and 1, 0 and 1 will be get added. Path.addEdge, path.addEdge, 0 and 2, then 0 and 2 will get added. Path.addEdge. When we'll be calling 1 and 3, then 1 and 3 will get added. Path.addEdge, 1 4, then 1 4 will get added. So in this way, whenever we'll be calling this addEdge, those vertices will get added. So we have to start the traversal from a particular node. So for that we have to call the, let's say we want to start the traversal from this node. So we'll be calling path dot, that was I think the, what was the function name? The function name was shortest path. So we'll be calling the shortest path. So path dot shortest path, we'll be calling path dot shortest path. shortest path, and we'll be passing the start node from where. So if you want to start from 2, we'll be passing this start node 2, and it will automatically execute all the things. And if there is print graph, so that is a part of, I think, main function, so that will automatically print everything. So this line, so after executing the main function from here, the graph will be entirely traversed level wise it will be traversing, and the entire distances from this to this to this, that will get traversed. I mean, from where we'll be counting, the traverse will be from there. So we have understood the shortest path algorithm by now. In next session we'll be dealing with the Dijkstra algorithm, and then onwards we'll be dealing with Bellman Ford algorithm. So do subscribe. We'll be meeting next session.